Let us discuss one more application of Gauss's theorem, that is electric field due to a uniformly charged spherical conductor. That spherical conductor may be either solid one or a hollow one. Hollow means interior is hollow. Whether it is a solid conductor or a hollow conductor, the charge given will be uniformly spreading on the surface only. So that is one of the speciality of the conductor. No charge can reside inside the conductor. Whatever the charge externally given, that will be spreading on the surface only. So this situation is a situation of uniform charge distribution, surface charge distribution. Let sigma be the surface charge density. We already studied surface charge density is equal to charge given divided by surface area. So let us take R as the radius of this conductor, spherical conductor. Then the surface area will be 4 pi r square. Therefore sigma is equal to Q divided by 4 pi r square, where Q is equal to sigma into 4 pi r square. Put as equation number 1. This equation gives the total charge given on the conductor, and the total charge given on the conductor Q is equal to charge density times surface area of the conductor. Now case number 1, electric field at any point outside the sphere. So this is a sphere where the charge Q is given, and let us consider a point P at a distance small r from the center of the sphere where electric field is to be obtained. In order to find electric field at this point P, I have to construct a Gaussian sphere. Gaussian sphere. Why Gaussian sphere must be constructed? Because the charge given inside is spherical in shape. The charge distribution inside is spherical in shape. Therefore, the Gaussian sphere also, the Gaussian surface also must be spherical in shape. So I constructed a Gaussian sphere. Around the point I have to take a small elemental area ds. This is a positive charge distribution, therefore electric field direction will be like this, and area vector also perpendicular to the surface, that will be like this. So E and ds are parallel to each other, that means theta is equal to 0. There is no angle between E and ds. Now let us apply Gauss's theorem. According to Gauss's theorem, total flux phi is equal to surface integral of electric field integral of E dot ds is equal to Q by epsilon 0. Now expanding integral of E ds cos of 0 is equal to Q by epsilon 0, because theta is equal to 0 in this particular case. So cos of 0 is equal to 1, therefore I can put cos of 0 is equal to 1, integral of E ds is equal to Q by epsilon 0. So that means E into integral ds is equal to Q by epsilon 0. Now what is integral ds? Surface area of the Gaussian sphere, and that will be equal to 4 pi small r square, because small r is the radius of the Gaussian sphere. Now I am going to substitute equation number 3 in equation number 2. I will be getting E times 4 pi r square is equal to Q by epsilon 0. That means E is equal to 1 by 4 pi epsilon 0 times Q by r square. In terms of vector, E is equal to 1 by 4 pi epsilon 0 times Q by r square into a unit vector r, where unit vector r is the unit vector pointing in the direction of small r or radially outwards. That will be the direction of net electric field due to charged spherical conductor at any point outside. If it is a positive charge, the direction will be radially outwards. If that is a negative charge, the direction will be radially inwards. Let us consider positive charge only for the theoretical explanation. So this equation gives electric field in terms of total charge. Let us substitute for total charge given. You already studied total charge given equation number 1. Q is equal to sigma times 4 pi r square. When I substitute that here, E is equal to 1 by 4 pi epsilon 0 into sigma into 4 pi r square divided by r square. 4 pi cancels. What remains? E is equal to sigma into capital R square divided by epsilon 0 into small r square. Sigma is a constant, capital R is a constant, epsilon 0 is a constant. That means E proportional to 1 by small r square only. What is the meaning of that? As the radius, as the distance of the point from the center of the sphere increases, electric field decreases. Electric field due to a charged conducting sphere decreases as the distance of the point from the center of the sphere increases. Okay, so this is the equation in terms of charge density sigma. This equation in terms of total charge given Q. So these two are the electric field equation due to a charged conducting sphere at any point outside the sphere. Now case number 2, electric field at any point on the surface of the sphere. On the surface of the sphere, you can see this particular figure. If I am considering this point on the surface of the sphere, I have to construct a Gaussian sphere also on the surface of the given conducting sphere. So that means at that time, this small r become equal to capital R. So that's the only change takes place on the surface of the sphere. You can see here, small r become capital R. When small r become capital R, electric field equation becomes E is equal to 1 by 4 pi epsilon 0 times Q by, instead of small r square, I have to substitute capital R square into unit vector R. Okay. So this equation gives total electric field on the surface of the sphere in terms of Q. Now in terms of sigma, I have to substitute small r is equal to capital R here. R square cancels. What remains E is equal to sigma by epsilon 0 into unit vector R. So that means electric field on the surface of the sphere is a constant. That means sigma by epsilon 0, sigma is a constant, charge density epsilon 0 is a constant. That means everywhere on the surface of the sphere, electric field is a constant, and that will be the maximum value of electric field into that sphere. Outside the sphere, what happens as air increases, electric field decreases, that we already discussed in this equation. As air increases, electric field decreases because they are inversely proportional. But on the surface of the sphere, electric field is a constant one. Now case number 3, what is electric field inside the sphere? Inside the sphere, obviously there is no charge. Q is equal to 0 inside the sphere. Even if I am constructing a point, I am considering a point here, and I am constructing a Gaussian sphere, and that Gaussian sphere will never enclose any charge. If the charge is not enclosed by the Gaussian sphere, there will be no electric field. So that means since Q is equal to 0, electric field inside the sphere will be 0. Now this figure shows the variation, graphical variation of electric field due to a charged conducting sphere. This will be the center of the sphere, and this is the radial distance on either side. Now the y-axis I am taking electric field, and you can see this is a radius, this distance is a radius. On the radius means on the surface of the sphere, the electric field become maximum, and the maximum value of electric field is equal to sigma by epsilon 0. Inside the sphere, there is no electric field at all. Nothing is there. Inside the sphere means in this particular region, there is no graph actually, because electric field exists on the surface of the sphere. As the distance increases from the sphere, outside the sphere, electric field decreases 1 by r square times according to this equation. So this figure or this graph shows the variation of electric field due to a charged conducting hollow or solid sphere. Actually, this is not a two-dimensional graph, it's a three-dimensional graph. Because we are not able to draw three-dimensional graph in a paper, we are just drawing two-dimensional graph only. But you can assume that, you can imagine that this is not a two-dimensional one, this is a three-dimensional representation.